done? Okay, we're set. Okay, hello everyone from the one in person here in London and from the one, I have the light of the projector in my eyes, and from the one online from Boston and all the rest of the world. So it's a really good pleasure for me to introduce Professor Marta Gonzalez. She's Associate Professor of Senior Regional Planning at the University of Berkeley. She's a research fellow of Lawrence Berkeley National Lab. I'm very happy to introduce her because she was my mentor during my second postdoc when I was at MIT. Actually, she introduced me in the urban science. That is now one of my major field of research. So I'm very proud to introduce her. And she's okay. Marta is one of the best researchers in the world in terms about mobile phone data. In terms of mobile phone data applied to understand our cities, whereabouts, city behavior, how people interact with cities. And she started as a physicist. Are you considering yourself still a physicist? Yes. She's proud to be a physicist. Although she moves to different faculties because she was assistant and associate professor at MIT and civil environmental engineering, and now she's within the urban planning faculty. And her work spanned from mobile phone application of how people interact with cities, and now focus either about energy consumption in cities, either pollution, and I think that one of the last work was either in fire hazard around urban areas.
Correct.
And so I'm happy. I will give you the time. 45 and whatever.
45 will
okay, thank you so much.
Hello everyone, thank you for being here. Today, the title of my talk is Towards the Science of Sustainable Cities, a Complex System Approach. And how I prepared 3 papers, 2 that have close, good stories, and 1 that is humbling, in the sense that it was very ambitious, and I have more open questions. It's still accepted for publication, but this latest one is like I'm a little nervous. It's the first time I present it. So the general motivation is that we gave up our privacy because internet became mobile. We leave digital twins, digital traces, and that have fundamentally changed businesses. Mapping on-demand mobility, even autonomous cars, but the common denominator is that it's unbelievable. We have it like neurons of a new global neural systems, digital traces everywhere. Then the question is, how can you use all that data that could use network science and AI together with the transportation system and the urban planning domain? So the idea is to come with these 2 worlds in which we not only do the data science, but we are keeping in mind what are the questions that the urban planners are caring about. That together is what I like to call city science, when you have computation and statistics and data, and you have the problems of the domain. Then, in that sense, I hope to navigate you through 3 stories, 3 papers on that realm. So the first is one of the round-up stories that it was nice result in the sense of that the goal was accomplished, and is urban dynamics through the lens of human mobility. It was published 2 years ago. And any guess? These are 3 cities. This is Bay Area, Los Angeles. The other 2 I don't remember. We are going to analyze 3 cities like that. Any guess what the bars represent?
Density of people.
Correct. Population density. So the first aspect as urban planning is, let's analyze many cities in the world. Let's compare the urban form and see if we can find some general rules to then, as a next step, continue planning the city. So at that time, we collected, and then we're going to do that, the urban form through the lens of one of my specialties, that is urban mobility. Then notice Atlanta is a textbook case of a sprawl city, And we have different cities from a largest population of 5 million to Alicante in Spain of half million people. And we see that they have different form. And for each of these cities, we have not only the population density, the area, and also the Gini. The Gini, unfortunately, is not the Gini of income inequality. That comes next. The Gini we are referring to here is the distribution of the population. That means low Gini is the population is everywhere in the area, and a higher Gini, like this in Shenzhen in China, means you have many more people concentrated. So you are thinking the income as a population density. Then we have one characteristic of how the population is distributed by the Gini of the population. We have the area and the total population. And because in these 21 cities, and how we selected just by data availability, that was basically the data I could have in my lab and my former postdoc that are professor, let's say in China. We have some collaborators in Spain. So the idea was to collect the largest amount of data we had already mobility data for. And for each of them, we calculated this very old metric that is the radius of gyration. We get the center of mass of the locations and the average distance of the locations to the center of mass. And what it conceptually gives you is the radius within which every person is most likely to be found. And because the locations weight like a mass, it counts where you are most visited. So we are not trapped, but that radius stabilizes and it capturing only one number, the characteristic footprint you have in your city. Then every mobile phone user have one RG, and for these 21 cities, we look into the distribution of RG. In the perfect world, this would be universal. However, the good news for the urban planning domain is that most of the people have relatively small RG. So we order our time to be mostly in home and work. And interestingly, we have some people that really commute between cities of different countries. So the first question would be, we would think that the largest RG belong to larger places. But here we have this outlier is Bogota. So we have a very tiny city in this context of the 21 that have an average RG of the entire population larger. Any guess why? Why is that? Why Bogota being so small have so large RG? Last time I asked the person that could answer that came from this global south. Any guess? The reason is what we are showing here is the distance from the city center of the different areas. And what happened in Bogota in particular is that the majority of the population live in the outskirts. That is the slums of the city. So that is a country that is into war. People is displaced, they come to the city, they could not live in the center, and there is a lot of population here. So that shift, the majority, it shifts the average RG to the right. Then one detail I want to mention is that we are using one RG per person, and I want to show you how is the temporal behavior of the RG. So this is 6 months of data. With 3 months already, everybody stabilizes within the group of your RG. So that is really a cool metric that is dynamic and a characteristic of everybody at the same time. Okay, we already learned that for some reason the RG doesn't depend on the area of the city. And then we go to see 3 cities at a time. And what we are showing here is by colors. So we are coloring, let me go first for the socioeconomic strata. As I mentioned already, green here is the poorest, blue is medium, and red is the richest group of the city. So we have, according to where the people live, what strata they belong to is the color. And for each of the groups separated by income, we calculate the probability of having an RG. And then you already have the division. As I mentioned, in Bogota, as expected, the poorer population have much longer trips. This is universal. That is one of the complexities when we're studying cities, that the universalities appear, but not always. It's not universal at all because, for example, in Los Angeles, we have here poor and non-poor Hispanic. So in the US, the division of how people live is not only by income. A lot happen by race. You have your neighborhood that depend on a given race. Then in LA, here is the majority of poor Hispanics, and this little star here is the central business district. Then, as expected, the PRG of the poor Hispanic is smaller. So in Bogota, we have the poor traveling a lot, and in Los Angeles, traveling less. And also in Boston area, we have the suburbs are wide and rich, and we have this tail here. So again, no clear universality between the RG and the income. However, when we do intercity and we measure this in COVID, yes, higher income travel more on vacation. So that is always is a caveat. The one thing is the commuting distance is not obvious. Economic segregation matters more. And then we came out with this idea, because it depends where you live, how much you're going to work. And then in this characterization of the urban form through human mobility, we came with this idea that is, let's divide the population, not by income, but where they live, respect to the central business district. So every city has an arbitrary centroid, that is what is the center of the city. Depending on how you live, we calculate the PRG. And this curve came something that allowed us to shape the story of this first paper, that is Los Angeles. It doesn't matter if you live 15 kilometers from the center of Los Angeles, you're going to have this curve of PRG. And if you live 3 to 6 kilometers, you're going to have this curve. All this curve kind of collapse. However, in Boston, if you live in the blue curve, 15 kilometers from the city center, you travel like this. But if you live 3 kilometers from the city center, you travel like this. Any guess why? What's different between Los Angeles and LA? Why they're doing like that? They are two American. We already saw that, this is not divided by income. What is the difference between Los Angeles? Let's see the
systems.
Huh?
Transport system.
Excellent. Yes, that could be the reason. But in this case, and I can tell you because I have the data of these cities, 70 to 80% of the census tract, of the people living in a census tract, use their own car. Only 20% use a transport system. So that would not, that's a good guess, but it's not the reason. Any other guess?
Population density.
The distribution of the population is, yes, it has to do with the urban form. And here is Boston. Look at Boston. And here is Los Angeles. So definitely it has to do with the urban form. And what happened is that the conditional probability of how much you travel and how far you live from the city center, it depends, it's very different if you have in what we start calling a monocentric city like Boston or a polycentric city like LA. So in a monocentric city, everybody goes to the center. And what happens is if you live 18 kilometers from the downtown, you have this peak in 18. Why? Because everybody's traveling to downtown. Fantastically, in LA, the scenes went different that everybody, so the distribution goes from this to this. And the tendency is that the first cities start monocentric and they transition to polycentric. Then we want to have this discovery, quantify it, and apply this question to all the 21 cities. How we quantify? We say, what is the PRG but the cumulative. For the people that live in the center, every city has one center, it's arbitrarily located. And what is the RG of the population and a distant R, and we are doing in concentric cities. And the idea is that we would have monocentric cities like this, everybody go to the center, or polycentric cities like this. And then what happens is, if it's monocentric, the difference between these RGs, it increases. However, if it's polycentric, all the curves collapse, is flat. Here is how far you live, and the KS is the Kolmogorov-Smirnov test to compare the distributions. We don't want the distribution to be equal, it's just a metric to compare the transformation of distributions. And here we have the contribution is that through the lens of human mobility, we can measure this delta KS from polycentric to monocentric. And another angle is, believe it or not, what was done in urban planning, that is urban centrality depending only in population density. In particularly, it would be equivalent to polycentric and monocentric, but we call it, to distinguish from mobility, compact and dispersed. And then we did this delta KS for the 21 cities, and we have textbook flat, like LA. The distribution is all the same, independent on where you live, or textbook monocentric, like Boston. And we have other cities like Wuhan, Rio, and everything in between. Then we have delta KS for mono to poly, and the Gini of the population density for a compact to dispersed. Interestingly, when we see this, so here is a distribution of the 21 cities of the world. When we see the average, what we see interestingly is that this region that would be compact and polycentric is less cities are there. And I know because I did already this for 15 only US cities, the most populated ones, most US cities are here, dispersed and polycentric. And the intuition would be, what is the best? So the question that we would like to ask best next is, what is better? We don't know yet. We know compact is good, it's less vehicles miles travel, but we don't know if it's better. Compact monocentric like Wuhan, or compact polycentric like Shenzhen. So then we were doing this during the COVID time. That's why it was so easy to gather all the phone data together. And then we could look how the urban form affect the spreading of the diseases, but of course we didn't have the mobility data during 2020 for the 21 cities. We only have it with Skido Dynamics, our collaborator is a company, of the 11 cities in Spain. Here is the incident of number of infected per 1,000 people in phase 1 of the infection. Phase 2, it was all quiet period, and then the mess in phase 3 in the fall of 2020. This is all in Europe. And the question is, we have the urban form of all the cities. Is the urban form a good predictor of the R0, the reproduction number of the epidemic? So this is very charged, but bear with me. We have here the 3 metrics. Delta KS, the urban centrality metric, the average RG of the entire city, and this is a variation of the KS is comparing to if everybody would be at home. So this is a KS-based metric as well. Then what we see is that we do XGBoost to predict the R0 with RG, KS, delta KS, log population, Gini of population. So all the variables that only are mobility or population. And this is phase 1, phase 2, and phase 3. RG, higher RG, higher R0, in the phase 1 is a better predictor. Then RG, when you are in phase 2, lockdown is not a good predictor, but delta KS is very sensitive. So in phase 2 of the epidemic, delta KS is a better predictor, and which means more monocentric. Interestingly, more monocentric have higher values of R0 in the phase 2. And we have in phase 3 again RG. So basically, we found a new metric to characterize urban form through the lens of urban mobility. We need other applications for urban planning research like transit development and other things that I would like to discuss with you. For the epidemic spreading, it helps when you have lockdown. And basically, we show that aspect I just mentioned, and the future work includes looking into the vehicles kilometers travel and CO2 emissions for different urban forms. That concludes my first story. Then let me go to a second data science story, that is how we deconstruct the laws of facility distribution in cities. And for that, we're going to use the road network, because you can go from one point of interest to another through the road network. We are not using traffic. We assume a free flow or distance in the road network. We have the population from land scan, and we have the facility. The method can be used with other point of interest, but we have the facilities from Foursquare. And we're going to pay attention to different cities, in particular, some already very established cities with a lot of point of interest, like in this case, Manhattan. And we have, in fact, New York City around Manhattan, Los Angeles and Boston, and we have cities that are being built, like in the Middle East, Riyadh, Doha, and Dubai. And the first question we want to ask, Foursquare, is it good enough? We have years of Foursquare. Then, because the POIs are statics and humans are dynamic, after long enough, even in the Middle East, this is the facility per kilometer square distance from the city center. We have of the order of 5 facilities per square kilometers to 2, but it's not too different, the amount of POIs, and we have different types. Okay, we have our 3 layers of data. And what we want to investigate is how the facilities can be optimally distributed in any city. Then we go to the literature, we go to the people we like to follow, like in this case, this relatively, 20-year-old paper of Gassner and Newman, that is optimal design of a spatial distribution in network. Newman showed, using Lagrange multipliers, that this is a beautiful paper, 2006. I use them in exams to my students. So I recommend PRE 2006, Optimal Design of a Spatial Distribution of Networks. No data, only Newman brilliancy show that in the US, you would have Landsat type of data in the entire US, and N facilities. The facilities he's distributing is using this Voronoi diagram. So we are showing much higher population density and N facilities less than the number of population centers. And he is able to show a method with Lagrange multipliers that show these amazing scaling laws that says the population density in each of these zones of Voronoi cells is proportional to the facility density. How is the facility density? 1 over the area. So the question is, you have your entire country and you have N facilities to distribute. What is the optimal distribution? The distribution goes not as the population density. If you put N facilities proportional to the population, you have the rural areas underserved. That's the problem. So you don't use a facility equal to population. You don't do it like that. That would be the lazy way. He shows that the optimal way is if you use population density with facility in which this goes to the row to the 2/3. And that is the way, is the theoretical view. Then it came 3 years later, a PNIS that used data to test. They didn't question the law. They just test how real facilities are distributed. At the country scale, in Korea and the US, they show that there are 2 types of facilities. The facilities nobody can live with, like a school. You need a school no matter how remote the data is. follow the 2/3 at the country scale in Korea and the United States. But not all facilities do that. As you know, obviously, you have more restaurants in Manhattan than in Missouri. Missouri is a state, but let me say like in South Bend, Indiana. So, okay, we have the commercial way to distribute facilities is end to the row, and we have this to the 2/3. Then we say, perfect, let's apply this to my question, that is cities. We want the 50-minute cities, let's apply the law of Newman to distribute facilities. Then the problem comes that it goes like this. Why it fails? And then he's not wrong. But in his case, this is the amazing thing, in his case, the condition for the demonstration to apply is that you have many more blocks in the city than facility to distribute. And the problem is that you have, imagine you are dividing Landsat data as I show you in 1 square kilometers, and you have your city. You have more restaurant or equivalent number of restaurants than blocks to distribute. So the dilute condition of facility distribution for the optimization of Newman doesn't work at the city scale. And then we were trying what is the ratio this is empirical, it's not the optimized distribution, and it's a mess. So we have not the 2/3. 2/3 is 0.67, it's nowhere. And we're having in the different facilities, and we're testing here, I think, hospitals, but we could do it with different facilities. Okay, it doesn't apply empirically, but then let's test it, the optimal distribution. I got all the hospitals I had in Foursquare, all the different facilities, and we would do, this is a block in your city. The links are the road network. Remember, that was my other layer, the road network between the blocks that gives me the road network distance. And I have all my banks, all my hospitals. And what we're gonna do is, for the existing hospitals in a city, how would they be located optimally? Something similar to what Vittorio showed in Alex's birthday. So you say it's a thought scenario. Let's redistribute everything. And then how do we do that? Is that this Wernicke algorithm is very old in terms of optimization. We use Gurobi, and basically what we do is, it's very easy because you have your network, you let the algorithm to wrap the things around, and what you have is the cost, is the road network distance, and the only condition is that you have is that for every block of population I, that is your Landscan cells, you have your facility J. And what you have is that you have less facilities than blocks. And then basically you are, imagine like a Monte Carlo simulation, you are swapping around such that at the end you minimize the total distance from the end facilities to the total population. One aspect that we take into account is that different blocks have different populations. So you are optimizing for different number of people. But then the keywords is, this is the algorithm, and we run it through Gurobi, and the cost is the distance through the road network. Then to tell you an example, so these are the little blocks of population I was talking about, and we have within this what we call service areas, one hospital. And this is the distribution in reality of all the hospitals in the Great Boston area, and the color is different cells have different number of people, remember the bars. And we have 80,000 people here served for only one hospital. And this is the ideal scenario where all the hospitals are optimally distributed. And in fact, we calculate the ratio, that is the travel distance in the optimal scenario versus the actual scenario. So if the actual scenario is much larger, then this ratio is negative, log of the ratio is negative, And then you have 10 times worse than the optimal. All reds are underserved. They have to travel too much to go to a hospital. And all green is 4 times faster than the optimal case. They are better served, overserved. So that is the ratio. And then we can evaluate that. Again, the actual distance and the optimal distance. What is interesting, and it was a surprise for me, is that we're showing here the bands, optimal and actual. And what are in the stars? Is one distance per city and facility type. We have every green is a facility type, and we have the distance in Doha, Riyadh, Dubai, New York, Boston, and Los Angeles. To my surprise, there is not huge difference between cities, but is difference between facilities. Like, for example, fire stations are relatively further away, let's say in Doha, Riyadh, and Dubai, in this is a particular case that in the 3 Arab cities there is different. But overall, what we see is that banks, pharmacies, schools have lower distance than soccer field, concert halls, and supermarkets. So we order them by the distance. So what is seen is that here is the actual distance that we observe in all the cities. What matters the most, and is not too surprising, is the density of the number of facilities by the number of occupied blocks in the city. This is the number of populated grids in the city versus the number of facilities. And then this ratio, that is the ratio of the two distance, changes more by facility type than by city. So far it was somehow a way to say that is somehow like a universal principle. It doesn't matter if you are in Doha or if you are in Dubai, the average distance for a bank is one way, the average distance from a fire station is another. So the number of facilities is like the unifying market. You have more banks than fire stations everywhere in the world. That is the type of thing. Okay, then we wanted to understand further, again, because the Newman law didn't follow, we want to find a law of the optimal distribution of facilities. But in order to keep our life better, we are not only going to work with real cities, and now because we are doing the optimal distribution, we can use many cities with their population. We can capture their urban centrality index. We didn't use the KS because we didn't have phone data. We use this urban centrality index by Pereira, Rafa Pereira. And you have cities like Paris that have urban centrality of closer to 1, or Melbourne that have almost 0. So higher UCI, more centrality, and we can create toy cities in which we control higher centrality, very sprawl centrality. Then we check what is the relationship between the density of facilities and the density of population. And this is the beta of Newman. Notice that when we have very few density of facilities, we have the 2/3. When we enter in a lot of facilities, it's crazy. This is the real cities. This is the toy cities. And then there is something strange because we're doing optimization, we have one variation that is the urban form, but we want to understand this further because we want a law of the optimal distribution of facilities. And what we discovered, always when you try enough, you discover some universality. So basically, we're having here several cities with their own urban form. We are distributing N facilities, and we show is what is a probability that we find what is the number of facilities, number of blocks with our facilities. This is hard to understand, but we have our population, we have our populated blocks, we have N facilities to distribute. We are doing Gurobi to distribute them optimally. So we have Mexico and facilities, Dubai and facilities. And then we count what is the number of blocks without facilities. And it goes like this nice function. Everywhere in the world, when we are in facilities up to 6,000, let's say. Then after we discover that, then we can also, inspired by Newman, do this calculation that is similar to what he does in his PRA paper. That is, what is the average distance of to a given bank or to a given facility if you have n? That is equal to, if you are in a population with, in a block with facility, is the size of your grid. And if not, is this function here that is just empirically found. And we have that the average distance to facilities, given the number of facilities, is this form. And this was because we found this empirical relationship. And then when we see in the toy cities and in the real cities, we have this very well-behaved law. It's clear that when you have something so well-behaved, it must be a way to collapse. And the way to collapse is multiplying by this alpha here in the x-axis. And what is that alpha? It's basically a constant over the number of occupied or populated blocks. What this contains is the urban form of the population density. So, why is so well behaved? Because it's a grid, and we are doing always an optimization problem. What is the difference between cities? The urban form. And then, once we have this form here, we can invert the function. And then we can ask the typical question that is, given a distance that I want, how many facilities do I need? And this is the empirical calculation, and this is the numerical calculation. Then we show, like for example, to have 1.5 kilometer distance to that facility, we would need about 100 in Barcelona and 500 in Los Angeles. So the urban forms affect the efficiency of the distribution of facilities. Then, so we uncovered the disparities in accessibility of facilities. We found that the simple scaling law doesn't exist at the urban scale, but we found that optimal travel distance can be modeled as the function of the number of facilities, and we can estimate the number of facilities to get a target accessibility. That is the second story. And here comes the final story. That is the one that, should I leave it here, Ricardo? Or
Yeah. What you mean, like the slides?
No. Keep going. Keep going.
No, I don't know. You meant the slide? Yes.
No, because I told two stories and
Yeah,
I have
you
one
can.
more.
You have time. There is
Okay,
no
let me tell you this one that
I
is.
agree here. Yeah.
It's
fine.
Okay, so this is
It's just Sophia that will have
a topic, and it's okay. So we have the RG story, the accessibility story that is very mathematical, and this is a new topic. I'm very eager to enter, and it's about data-driven planning and modeling in wildfire research. So to give you some context, if we see the number of fires from 1985 to 2015 is constant, more or less, fluctuates a little. But it's not that we are having more fires. We are having the area burned much higher. And in this plot here, we have from 1982 to 1991, we have the area burned, while we have from 2010 to 2019, it's getting much worse. Of course, if you have one fire and it burns much higher, you have that the cost from 1990 to now is even in, let's say, 2015, it was 3 billion in cost for wildfire. So why the wildfires are getting
It's
bigger?
California. Left. Only California or
Yes, this is California, and in this case it's federal, and this is California. Yes, this is data from the US and California. California there too, yes. But then, exactly, in the case of California, what's going on is that I already told you that LA was the textbook sprawl city. And what we have is that what is happening is that we have the wildland, we have the city growing, and as I told you, it doesn't grow dense, it sprawls. And then we have the wild-urban interface. Then, in fact, when we see the number of regions that in which we have houses that are in the buoys, wild-urban interface, incredible. All the orange census tracts have houses that they are wildland and urban interface. That is why right now, if you have a house in California, the insurance are dropping you. So this is a topic you could do working in environmental science, but if you work in cities, is climate-related problems, insurance-related problems, price of housing is a whole problem. So then, entering, and the other thing I have here is, again, the area burned over time. So basically, what happened is once it entered the urban interface, it's much harder to control, it goes gray. And then we have from the 70s to the 80s, of course, we have the fire season, always the fire season, but you see the bars higher. So fires are equally frequent, but are becoming more harder to control. It has to do with urban going into the wild. Then the project we want to study here is we want to predict wildfire behavior, intensity, and spread. Because being in California is crazy that once the fire starts, you never know when it's going to end. Why? Then we enter to study this with the modesty of a physicist. Then, the first thing I've learned, and the reason I'm showing you this because I want to recruit brilliant minds like yours to this very hard, humbling problem. The first things I learned that in the modeling of fires, of course, as usual in life, it depends on the scale. If you are working with heat, oxygen, and fuel, you are talking about the physics of fire. That is super hard. There is, to my knowledge, no simulator that have really like the physics of fire and simulating what is happening in Los Angeles. If we go into the days and months, it's the semi-empirical models. And if we go longer time, it's called about fire regime, how it's going to happen. So this is other type of scale. What we're going to be working today is the fire spread models with semi-empirical models. Then, why the model stays? My own postdoc, he did his PhD modeling fire. And right now, to do a model like this, like it's a cellular automata, you only need to know what is the rate of spread, meaning how many meters per minute. So how fast the fire goes. What it depends on? It depends on, basically, in a few words, characteristic of the fuel, so what type of terrain you have there. You have the wind, the slope, and how dry it is. So you have moisture content, fuel type, what type of vegetation you have, wind speed, and wind slope. That's it. And that is going to tell you how fast the fire goes. This is called the Rothermel mathematical fire spread equation. Is from 1972, more than 50 years old, and it depends on the classification of fuel. For example, for the US, we have 40 class fuels to do the fire spread. Then this model has been there for a long time. And basically, I tell you the red in one direction, but then you have the red in the other flanks and also to the back. So it's in the semi-empirical model, you have your rate in the 4 fronts and depend on that equation I just gave. And then we thought, well, come on, if he's 50 years old, we can do better, right? So let's try to do this. And then basically, we needed to study the empirical models as they work. Basically, it follows, it's very cool. You have ellipse, and you have your terrain, and of course, in every ellipse, it's going to follow one different direction. It's the Hughes principle. And believe it or not, the shape of the ellipse, remember, this R is the formula I told you. They go from the shape of the ellipse that gives you the R, and the R tells you how all the axes of the ellipse are going to go. And LB is the length to breadth ratio, and these are the wind speed. Why? Why it works, and believe it or not, is this, you have the R that came from physics somehow, and the shape of the ellipse was like that. It's very hard to understand, but it's what the actual simulators, I promise, they use that. And then Cristobal from Chile, he did his PhD, and he created, during his PhD thesis, cell to fire. That is a cellular automata model that implements the Rothermel equation, but they don't go in the continuous. They do the law of ellipse growing in a cellular automata model that they have the advantage that is much faster, is parallel, you can do it in parallel, and most important is open source. Then you get all the typical input from our cell to fire, that by the way, we have it in HubeNet, cell to fire, open source. We need to have the wind. We have the slope, the elevation. We even have canopy from trees, but we don't use it in this part of the talk. And this is the type of output of our simulator that have the tree, the rate of spread of the tree, the propagation tree, the born probability, and we have our nice cellular automata. And here it comes the problem. This was cell to fire was implemented in Chile and Spain and Canada. And here we have an example that one fire scar that happened in Dogrip in 2001 that they, so where was ignition? 90 minutes. Where was the fire? 210 minutes, so on and so forth. So we have this fire behavior, and the standard non-open source simulator is called Prometheus. And the problem is that we have the actual fire scar and the Prometheus result. Our cell to fire, as originally done by Chris, didn't work, and we needed to enter some black box optimization of the shape of the slopes, and we ended up having, but one important thing to clarify. In order to have our cell to fire with black box optimization, we did not use the actual fire scar. We only work at the shape of the ellipse in these semi-empirical models, and we have the simulation. And when we see the comparison, well, basically, just by the eyes, you see that the new cell to fire with black box optimization is better. But we have, let's say, Prometheus underestimated all this region, overestimated here, original cell to fire super underestimated here, our new version of cell to fire did a little bit better, and this is very important because this is what is called the fire scars. Here maybe some houses. So our F1 was better, And at the end of the day, the open question, and that is why it's humbling. So basically, we worked and we implemented, we got better reproduction of the fire scars, but at this point, we don't know the why. Why this shape? Why this strange shape to model the spread of fire? It's an open question. One delta in that direction is we were checking the head rate of spread in our simulation and to really check if all the parameters are necessary. And the lesson learned is that from the 20 or so parameters, 3 of them are the most important. Which are they? The moisture content, the wind speed, and what is called the load, which is depends on the fuel type. So 3 parameters would be enough, and there is a whole open question of how can we develop this ellipse growth for fire spread simulators. That is why nowadays you have the LA is burning. They don't know how it's going to go the fire for how long. Because the physics in itself is very hard to understand, the physics of fires, and the semi-empirical models have a law that was developed in the 70s. So I would like you to tackle this type of question. So we could generate our own open source. It gave a relatively good F1 score. With the CHAP analysis, we found the 3 more key factors. By no means we revolutionized the area. We worked with the same equation that it was there. We could not develop a better one. Still is going to appear sometime later this year. And this is the conclusion. We introduced a new metric for urban form. We found universal form for the for the accessibility of facilities, and we made some progress in a cellular automata model of wildfire. Thank you so much.
Okay. Before asking questions from the students and the people that are here online, I have a question regarding the prediction.
Yes.
Because it is better to overestimate, like you have online, it's better to overestimate than underestimate the scar. So from a point of view of like,
exactly.
So this is just a curiosity from like emergency rescue.
It's better to overestimate.
Okay, so it's better your model.
Exactly.
Okay.
No, that's why, because you better evacuate and be wrong than don't evacuate.
Exactly.
Yes,
No,
I agree. So that
it's better to have an excuse to move people out.
Yes.
But if you have limited resources.
Yeah. So we need better models. It's not perfect, but at least we get wrong overestimating.
Yeah.
So yes, the benchmark simulator from the US is called Farsight. For Canada, it's called Prometheus. In Chile and Spain, they use similar to Prometheus. And now we have Cell2Fire, in which it was born for Chile and Canada. And now we implement it in this scientific report for the US. So I'm only showing you this result of the real time scar, but of course we did a lot of comparison, Farsight, us. And that is how we optimize the ellipse shape, and we have this Cell2Fire BBO. But yes, it's fascinating, and it was fascinating and humbling at the same time. However, if more people working on this, we could have, let's say, this multi-layer network, evacuations, and the whole digital twin with also the real emergencies.
Okay, question from here, and then from abroad.
I just have a quick question on these figures. It's really interesting that, you know, throughout the newer models, you reduce the underestimated areas in the northeastern part, but on the bottom top right. But bottom left is consistently underestimated. It's really interesting. I'm not sure if it's because of the...
This part.
Yeah,
right?
exactly.
The
And
front.
for all of them, they
Yes.
did not explain
yes.
at all.
Yes.
I just wonder. I don't know.
I know I have been in conferences where people have been working on these topics long time ago, etc. Semi-empirical models are a limitation, but more than that, one big limitation is what they call data ingestion. And one super hard aspect to have good data from at high resolution like this is wind. So, because we are using all the same input, of course, for the 3 simulators, I think this problem has to do that the input of the data on the wind was not what that was happening in reality. And the whole wind modeling goes into cloud modeling. So it's very complicated. I was like mind-blowing. And I say, okay, I need to do a new PhD. I need to continue working on this. But it's fascinating. And then, lesson learned, we need more than ever high-resolution data on wind to predict this is very good catch.
I have a question on the slide where you show the optimized distribution of the facilities.
Yes.
I think it was the second.
Oh no, Ricardo, what I do it?
Yeah, I don't get to change the sharing screen.
You learn already?
Let's put this. Sharing, that is okay.
Because I wanted to
Yeah,
move
you can in
quickly.
this way you can move quick and
Thank you. Optimal distribution is the second paper.
Yeah.
This?
No, it was like up, a little bit up.
Or you see the Newman one?
Yeah, the
20,
first one,
26,
the hospitals in Boston.
This.
26.
Yes.
Yeah.
Nice, I like this.
I just had a question because I see that in the center there is like an hospital that still gets like 80K of population using it.
You mean in the real or in the optimal?
In the ideal version.
This.
So I was wondering, like, so it doesn't like consider in any way the people using it. It's just based on the traffic.
Perfect. We are using distance. We do not change the population distribution of the city. We play with the facilities. One limitation that we have on this is we don't take into account the demand over supply.
Okay.
Yes. So basically, we have a lot of people here, and yes, it's, the capacity would be the next step into this story. So actually, because this was very much discovery based, okay, we wanted to do Newman law, it didn't work. We tried to came with a solution because imagine a paper, oh, we tried this and it didn't work. Sadly, it should, right? It should. We hope to be able to say the bad stories, but we really wanted to find the law. However, now that we found the law, we want to develop the applications. In fact, this type of facility allocation with Cristobal, the postdoc that did Cell to Fire, we have a paper that is given the rate of spread of the fire and the existing allocation of the fire stations, where are the places that have high risk of fire and they're too far from a fire station. And we did the same Gurobi optimization allocation, and we have one map that has actual location of the fire station, optimal location of the fire station. And the best way to work on this topic, as opposed to Vittorio and I that we relocate everything, the best way to do is you have N fire stations today at K. If you have a budget of K new fire station, where would you put it? That is the best way to address this. Then I think working more in this type of allocation of facilities is one way that we could go perhaps into the, for emergencies is one aspect, but for 15 minutes is a good
It's difficult to move facilities, either shops.
yeah, but you can add.
Yeah, you can add and shape their, there is a word from economics, there is like the basin of activity or something like that. The reachability of each of them, you shape it in different ways. It was Andrea's time.
Yeah, maybe it's also a short question actually on this exactly. Maybe, I don't know, maybe it's very obvious because I don't work in this field. I was just wondering, so this travel distance, so is literally the distance like that you would take, for example, in a car between 2 points? Or is like you take into account for transport or not? Like how do you measure this? Because I was thinking like depending on the kind of city, this can be very different. Like,
Very different, yes.
so
That's why
I don't know if it's like there are other ways to measure, like
you know that one natural way is called travel time, but because we are not taking into account traffic nor mode of transportation, this is road network travel distance. That's it. Adding, yes. It's almost like a shopping list of things we need to add. We need to add, and you're right, are very good referees. Adding the limited capacity of the facilities is next step. Adding a mode of transport is next step, definitely. But for now, one addition into the topic is at least including the road network distance. It's the first step towards that. And then you need to add a mode into your road network. Good catch.
Any other questions, guys? Yes.
In the first paper, just so we have a
Yeah,
question
it's
about
really a question about
I was yes, thank you.
So when you were talking about like how urban farm affected like the spread of COVID,
Yes.
and then you differentiated between the different phases. I was wondering if you also thought about like, or because in the first part of this talk or this presentation, you were talking about like socioeconomic differences that you took into account. And did you take that into account here and accounting for like socioeconomic differences, or like I know you had the different
No,
but
actually, in my last slide, I changed this. When notice that this is just because, as you know, I'm working a lot in CO2s and urban form and planning. But the actual real second item I said here that it needs to be done is to take into account the incidence rate per census tract or per demographic group. Because the problem is the data we had was just temporal. Every city is one.
Yeah.
So we did not find, from where we were in the US, this number of cases at the zone level or more detailed level. But it matters a lot, for sure.
in the beginning, I'm trying to remember, but I think you. Yes, thank you. Yes, this yeah, because that's what I was thinking. So because when you said that RG predicted like phase 1, and then if RG is determining socioeconomic segregation, then
I
it is
know what
kind
you
of
mean.
interesting that
Let me think. Yes, because we knew, for example, in Bogota, these people travel more. And what happened is that overall, in a city that you have large energy, we have better predictor of the R0. But mobility, census data, we have spatially distributed. Unfortunately, cases of COVID we did not for the Spanish cities that we were having the urban form. Yes, it's a whole topic of how to do the population density. Yes, it should matter. So this deserves a study taking into account the spatial distribution of the incidence cases. We did not have that. Yes, it almost brings together the last paper and this paper. We need better data. So it's never enough data, right? Because even the number of cases, we want them spatially distributed. It's not enough knowing all cases in Bogota, all cases in LA. It matters to be where, right? And to understand the urban demographics.
And one more question. So I guess it's a two-part question. So you showed kind of geovisualization of the houses like urban wildlife interface.
Yes.
Do you know about the demographics that tend to live in that?
Ah, great question. To be honest, in LA is the richer houses. Yes.
Super fun.
One for one. Finally.
We may not be rich, but
It's not about that. It's more about the insurance. So they are able to cover themselves.
but then they
They should be able to be covered.
In the LA area, so again, no universalities in terms of the spatial distribution of demographic incentives yet, but in the LA area is the hills is the richer. Sad part, in the paper I told you of 5 station facilities, very vulnerable regions are rural areas. And in rural areas, as we know, in California, the income decreases. So in the high density places of LA is the richer, the more expensive houses, but we need to keep an eye on the rural areas of California.
Because even with the different models, I was wondering if, given whoever's more vulnerable to like on this wildlife urban interface, which model is predicting impact on like what demographic, right? So like in the case of like rural areas that have less access to fire stations, which models, perhaps like the third model that you choose for ellipses, that one's kind of underestimating the impact for that demographic, but then for the rich people like LA, perhaps they're being overestimated more, but
Yeah, that's interesting. Yes. And another aspect I didn't mention is that these whole semi-empirical models, as you notice in the R, is everything about the fuel types that have to do with vegetation. Wood houses, and in the actual houses, they got crazy. So it's even harder. So it's a whole topic of very relevant science to be done. Why we don't study in physics this? I wonder. It's too semi-empirical, I guess. No, in fact, one expert in Berkeley is Mike Goldner. He's mechanical engineering, typical from the scientists. He's not interested in the semi-empirical models, he's interested in solving the physics of fire. Very, very ambitious. But also, if we say that computation was a problem, that should not be the problem anymore. So yes,
There should be some
that is
AI
the whole.
stuff for the simulation.
But there is a whole department that works in this topic. It's called forestry, and they are not doing the physics models. As usual in every research question, there are communities.
Guys, let's thank Marta again. She will be with us for a beer, I think.
Yes.
Yes. Okay.
The line or the
No, they are checked.